Welcome back to the channel. Today we're diving into one of the most intuitive and powerful algorithms in machine learning, decision trees. If you've ever played 20 questions or followed a flowchart, you've already used the core concept behind decision trees. By the end of this video, you'll understand exactly how they work, when to use them, and why they're so popular in data science. So, what exactly is a decision tree? Think of it as a flowchart that helps us make decisions by asking a series of yes or no questions. Just like when you're trying to decide what to wear, you might ask, is it raining? If yes, take an umbrella. If no, check the temperature. Is it cold? If yes, wear a jacket. If no, wear light clothes. In machine learning, a decision tree works the same way. It's a tree-like structure where each internal node represents a test on a feature, each branch represents the outcome of that test, and each leaf node represents a final decision or prediction. The tree learns these questions from training data to make predictions on new, unseen data. Let's break down the anatomy of a decision tree. At the top, we have the root node. This is where we start with our entire dataset. As we move down, we encounter internal nodes, which represent the decision points or tests on our features. The branches show the possible outcomes of each test. Finally, at the bottom, we have leaf nodes. These contain our final predictions or classifications. For example, if we're predicting whether someone will buy a product, the root node might test age greater than 25. The internal nodes could test income greater than 50,000 or previous purchases greater than 3. The leaf nodes would contain our final predictions, will buy or won't buy. Now, how does a decision tree actually learn from data? The process involves 3 main steps. First, we select the best feature to split on. Second, we partition the data based on that feature. Third, we repeat this process recursively for each subset until we reach a stopping condition. But how do we choose the best feature to split on? This is where mathematical concepts like information gain and Gini impurity come into play. The algorithm tries different features and chooses the one that best separates our data into distinct groups. Essentially, the one that reduces uncertainty most. Let's visualize this process. Imagine we have a data set of people with features like age, income, and education, and we want to predict if they'll buy a luxury car. The algorithm might first split on income because it provides the clearest separation between buyers and non-buyers. Then, within each income group, it might split on age, and so on. Let's work through a concrete example. Suppose we want to predict whether to play tennis based on weather conditions. Our features are outlook, sunny, overcast, and rainy, temperature, hot, mild, or cool, humidity, high, normal, or wind, strong or weak. Our target is play tennis, yes or no. Here's our training data with 14 examples. We can see various combinations of weather conditions and whether tennis was played. The decision tree algorithm will analyze this data to find the best way to split it. The algorithm starts by evaluating all possible splits. It determines that outlook provides the best initial split because it most effectively separates the yes and no cases. When outlook is overcast, we always play tennis, so that becomes a leaf node. For sunny and rainy conditions, we need additional splits. After analyzing all possibilities, our final tree looks like this. If outlook is overcast, play tennis. If outlook is sunny, check humidity. If high, don't play. If normal, play. If outlook is rainy, check wind. If strong, don't play. If weak, play. Decision trees come in 2 main flavors: classification trees and regression trees. Classification trees predict discrete categories like spam or not spam for emails. Regression trees predict continuous values like house prices or stock prices. The main difference lies in what the leaf nodes contain. In classification trees, leaf nodes contain class labels or class probabilities. In regression trees, leaf nodes contain numerical values, typically the average of all target values in that region. Decision trees have several compelling advantages. First, they're highly interpretable. You can easily explain the decision-making process to anyone. Second, they require minimal data preparation. No need to normalize features or handle missing values extensively. Third, they can handle both numerical and categorical data naturally. They're also computationally efficient, can capture nonlinear relationships, and automatically perform feature selection by choosing the most important features for a split. Plus, they provide feature importance scores, helping you understand which variables matter most for your predictions. However, decision trees aren't perfect. They're prone to overfitting, especially when they grow very deep. They can be unstable. Small changes in data can result in very different trees. They also tend to be biased toward features with more levels and can struggle with linear relationships. Overfitting occurs when the tree memorizes the training data rather than learning generalizable patterns. This happens when the tree becomes too complex, creating very specific rules that don't apply to new data. The result is high accuracy on training data, but poor performance on test data. Fortunately, we have several techniques to prevent overfitting. Pre-pruning involves setting constraints during tree construction, like maximum depth, minimum samples per leaf, or minimum information gain required for a split. Post-pruning involves building a full tree and then removing branches that don't improve performance on validation data. Key hyperparameters to tune include max depth, min sample split, min samples leaf, and max features, number of features to consider for each split. Proper tuning of these parameters is crucial for optimal performance. Decision trees are widely used across industries. In healthcare, they help diagnose diseases and recommend treatments. In finance, they assess credit risk and detect fraud. In marketing, they segment customers and predict purchasing behavior. In manufacturing, they identify defects and optimize processes. Some notable applications include Microsoft's use of decision trees in their Xbox recommendation system, banks using them for loan approval processes, and medical systems using them for diagnostic support. Their interpretability makes them particularly valuable in regulated industries where you need to explain your decisions. Let's recap the key points. Decision trees are intuitive, interpretable algorithms that work by recursively splitting data based on feature tests. They're great for both classification and regression tasks, require minimal data preprocessing, and provide valuable insights into feature importance. While single decision trees are powerful, they become even more effective when combined into ensembles like random forests and gradient boosting. These techniques address many limitations of individual trees while maintaining their interpretability benefits. That's exactly what we'll cover in our next video. If you found this explanation helpful, please like and subscribe for more machine learning content. Drop a comment below with your questions or let me know what algorithm you'd like to see explained next. Thanks for watching, and I'll see you in the next video.